Okay, well, welcome to the Solid State Seminar Series. It's my pleasure today to invite our speaker, Professor Eli Yablonovitch. Eli is a Professor Emeritus in EECS and also a professor in the graduate school here at UC Berkeley. Eli got his Ph.D. in applied physics a few decades ago from Harvard. And then he spent 2 years at Bell Labs, and then went back to Harvard as an assistant professor. He then decided to move to industry. He spent about 15 years or so in industry, first at Exxon, and then at Bell Corp. He moved to UCLA in 1992. And we were able to finally recruit him in 2007 to our department. And Eli has had many important contributions over the years. I'm going to just highlight a few. He was the first to introduce the idea that strained semiconductor lasers could have superior performance due to the band structure engineering and the reduced Hall effective mass. He's the father of the Photonic Bandgap, coined the term Photonic Crystal, foreign square that we use pretty much for everything, all solar cells, which is the light trapping factor. He introduced it, and that's often, the foreign square is often referred to as Yablonovitch Limit. He also has had actually many important contributions to processing of materials, and he developed an elegant way of transferring thin films, layer transfer of thin films from 3-5 substrates onto glass and other substrates. And that really enabled some of the highest efficiency single junction solar cells, gallium arsenide solar cells. He has won, he's a member of the National Academy of Engineering, National Academy of Sciences. He has won many awards. I'm just going to list a couple of them. Benjamin Franklin Medal, IEEE Edison Medal, Isaac Newton Medal, among others. So it's truly a pleasure to have Eli here. I think this is the best attendance that I have seen for a solid state seminar series. I think the key is you have to retire, and once you retire, if you're Eli, then what you will see is your popularity actually exponentially goes up. So with that, let's welcome Professor Yablonovitch.
See, I'm a little worried about the people standing at the back, because it puts a lot of pressure on the speaker. It's got to be a really good talk to be worth standing for the whole talk. Now, usually people are too bashful to come to the front, but even the front seats are taken. So I have no solution except maybe leaning against the wall. But the good news, it's a short talk, so I'm very glad you had a long introduction. I don't have that many slides. I have a very basic idea, and as soon as you get the idea, it'll strike you. Okay. So, as we heard Professor Javi mention, I was the first one to go searching for a photonic bandgap, which is we normally have a bandgap for Schrodinger's equation. That's the famous bandgap of silicon and semiconductors. And I thought, well, it should also work with Maxwell's equations, that you could also have a bandgap, but we didn't know the structure. So I'm going to describe how I searched, and it was a very hard search, and it took 4 years. I did eventually find a photonic bandgap, but now looking back in time, there was a much easier way to do it. And probably if anyone was in that position, they would do it the new way. And the new way involves the mathematics, so I'm actually going to have 3 or 4 slides of math. Now, even people who are mathematical physicists they said, oh, you're very brave even to show one slide of math. So I'm going to do my best. It's an experiment. We'll see if it works. But there's going to be some math that I'm going to have to show you. Now, when I was looking for the photonic bandgap, I tried various structures, and I was literally using what's called the Edisonian approach, named after Thomas Edison, and he was very famous. He said, try everything, which doesn't sound like it's very smart, but there was one thing very smart about it. Try everything, but make sure you have a very rapid test that you can, whatever crazy idea you have, you can test it very quickly. I couldn't test it that quickly. And the real problem was fabricating this, and I had the advantage of a machinist. So just like we used to have here at Berkeley, the machine shop used to be free, but that was a long time ago. Okay, and well, at Bell Labs, the machine shop was free, and so the machinist kept trying things, and they didn't work, and we tried something different, and didn't work again. And so he ended up drilling a lot of holes. And I'll show you some of the structures he drilled. And I sat down once and tried to calculate over that period. And it wasn't a period of 4 years, maybe it was a couple of years. But he ended up drilling 500,000 holes before we found something that worked. And but you shouldn't feel too sorry for him, because he had a cup of coffee, numerically controlled machine tool. He just drank the coffee. The tool did everything. But we didn't, for a long time, we had to have faith. We didn't succeed. So we first made this structure. And this one was basically a phase center cubic structure with spheres. So you had these little spheres that were about a 1/4 inch diameter, and we laid them out in a phase center cubic structure. Unfortunately, we thought it worked. Actually, though, this is the one that we thought worked. It's the same thing with spheres, but air spheres, and the space between the air spheres is filled with this white dielectric material here. And this is a ceramic material, and I was sort of clued in at that time, is I knew that I could use, of course, the higher the refractive index, the easier it is to make big band gaps. So I said, I have access, in the end, I'll have access to silicon, I'll have access to gallium arsenide, and they have a refractive index of 3.5. Now, if you had your freshman college, you're taught about a refractive index of 1.5, maybe you're comfortable with that. But 3.5 was available, so I bought an engineered ceramic that had also a refractive index of 3.5, a dielectric constant of 12, which translates to a refractive index of 3.5. And I drilled all these holes, and I actually published it, and then some theorists jumped on me and said, no, it's a pseudo gap, it's not a real gap, so that's a problem. And then they suggested to me that a sphere is too simple a unit cell. And so something to learn is that if you have FCC phase center cubic, it doesn't really tell you what the structure is, because you could put any object, and as long as it is centered on phase center cubic points, it's still a phase center cubic crystal. But then what is the object that you put there? And the object was similar to diamond. Diamond has 2 spheres inside the unit cell. And that's what it takes to get diamond structure. So, or 2 voids, if you like, 2 voids per unit cell. And that whole process took 4 years to get to that point. And you can see how it's drilled, and it's kind of a beautiful structure. And I remember testing it in the lab, and then I took it to a photo studio and had these pictures made. So the photo studio normally where you go with your family pictures and so on, but they were willing to take a photo of this structure. So this is the structure that ended up working, and it looks a little bit like Schrodinger's equation in that you have some derivatives on the left-hand side. The wave function, in this case, the wave function is the magnetic field, and could be an AC magnetic field. And, well, it's AC, it's got ohmic in it, so it's AC. And You can even regard this as being the eigenvalue. So it's a little bit like Schrodinger's equation. And here's the structure, which actually I suppose I should have brought. It's in a drawer, and I save it for occasions like this. But it's in a drawer in my office on the second floor. But this gives you sort of a pretty good idea of what it looks like. So that was kind of the hard way to do things, and we ended up with we finally ended up with a photonic bandgap, and there was a big deal. And I can tell you the editor of Nature wrote an editorial saying, "Oh, that was when we were stuck with the pseudo gap. Too bad it didn't work," and so on and so forth. And I exchanged some emails with him, but never get into a fight with the editor of a newspaper. As they say, they buy ink by the barrel, and so he could twist things to make it look like he wasn't saying something foolish. Anyway, so now time has gone by, and we should ask, did you have to do it this way? Did you have to use inspiration and intuition and trial and error? And no, today we have mathematical methods. I could have done this probably in a much shorter time. And so this is a rhetorical question. Is there an automated mathematical procedure for designing photonic crystals? The answer is yes. And this automatic procedure is also good for anything else you want in electromagnetics. And there are a lot of things we need in electromagnetics. So it's great if we have an automated method. So I'm going to get the idea, get rid of the inspiration, get rid of the intuition, and just follow your nose mathematically and come up with the three-dimensional dielectric structure. So to do this, you see this is a little bit of a complicated view graph. And let me tell you what the problem is. You know what you want to get. You want to get a photonic bandgap, let's say. Or there are other things you might want to get to. And you want to optimize a shape that will achieve that goal. Now, how many variables are there in a shape? Well, it depends upon how carefully you want to specify it. But a shape, you could have 1 million variables to specify a shape. And now you're stuck trying to optimize 1 million variables, which sounds like it's completely crazy. You'll never do it. Let me give you an example of what comes up. I'm an old laser jock, and when I first learned laser, they told me, here's how you make the laser work. You align the front mirror, and then you align the rear mirror. When you align the rear mirror, of course, that misaligns the front mirror. So then you have to go back to the front mirror, realign that. Oh, now that misaligns the rear mirror. You go back. So you go back and forth, and about half the time you converge and end up with your laser is aligned, and about half the time it diverges and the laser gets worse and worse. So that's if you have 2 variables. Imagine you have 3 variables. Then you got to align one, and then you got to align the others, then you go realign the others, and so on and so forth. It would, 3 variables, that's pretty much the most you can hope to do. But we want to optimize 10 variables, 100 variables, 1,000 variables. So there is a method, a mathematical method for optimizing 1 million variables. Co-optimizing. The point is that you don't have to necessarily go back and forth, and you just go fairly directly toward an optimum. So you co-optimize 1 million variables simultaneously. And it's kind of a neat method, but involves a little bit of math. And it has various names. We'll go over the story about the name of this mathematical method. But it uses the most reliable way of getting optimums. So for example, when you're a freshman in college, you learn calculus. And the most important thing you learn in calculus is how to optimize a function of one variable. You set the derivative equal to 0, and then you're at a peak. Or maybe you want the least of something, and you're at a minimum. Okay, so either way, you set the derivative equal to 0, and you get an optimum. And as soon as you have multiple variables, the student stuck. How do I do multiple variables? Because I'd have to go back and forth. But there's a way to think about this, and that is that let's say you have a figure of merit that you're trying to optimize, and you take the gradient, the local gradient, and it pushes you toward a, let's say you want to go up, so you look for the most positive local gradient, then you go up, and then you look for another gradient, then you go up and keep going up, always steepest descent. It's like being lost on the hills behind me in Berkeley, and I'm lost. I don't have my GPS. You just find the nearest road. If it goes down, take it. If it doesn't go down, don't take that one. Okay, and eventually you get back down to campus. So that's the method of steepest descent. But it does require a knowledge of the local derivative. And so when I'm up in the hills, the local derivative is how steep the street is. And so you just find the steepest street going downhill. So that's the method of steepest descent. So that'll be essential. But we need to have a way of getting the local derivative. So first, let me show you what the method is good for. This is sort of an example, and it repeats. I'm sorry that it repeats. You're trying to design a splitter for silicon photonics. So silicon photonics is very hot because they figured out that that you need to do optical communication inside data centers. There's a huge burden of internal high-speed communication inside data centers. And so they need silicon photonic components. So suddenly silicon photonics is kind of a big deal because it enables artificial intelligence. So one of the simplest things you can do in silicon photonics is to design a splitter, an optical splitter. And so here, and you start with a guess. The guess is it should just be a linear taper. And so you let that be your starting point. And then your figure of merit is how much power gets, or single mode power gets out of the splitter. It's a very efficient splitter. And we don't know the shape. Here's just a linear taper. We don't know if it should be linear. So what you do is you optimize the width of this taper, and there could be like 20 variables. So now you're trying to optimize 20 variables, okay? And you go ahead and you have multivariable optimization. So you have to have the gradient. I'll show you how to do the gradient. Then what happens, you look at the merit function. Merit function is the transmission through the splitter. And you see we're getting up to 90%. And we're doing it iteratively. So we normally do things of this type iteratively. And like you go down a street in the hills, and then you go down the next block, and so on. And finally, you end up at like 99.7% throughput, which is like terrific. And so that's excellent. But the program, it varies the shape. So you see what's going on here. It's varying the shape as it's running through the iterations. It varies the shape until it converges on an optimal shape, and the optimal shape is right there. Well, if I had a way to stop it, but anyway, you get to the optimal shape, and you monitor the throughput in the splitter. And so this is sort of an example. It's an easy example, but it's not that easy to get such a tiny, tiny insertion loss. Okay, here's another example of something that you might want to do, and that is, and it applies to the previous case, is you want to have the green is the desired mode. So you want to do mode matching. So you want to have a perfect single mode. The perfect single mode is in green, but unfortunately, what you're getting is this red thing, which is it's too peaky. And you say, well, what is the error in that case? Well, the error is you add up the mean squared of the difference between what you were trying to get and what you actually have, and that's the mean square error. So the electric field minus the desired electric field squared, and that's your figure of merit, which I'm going to call G. And you have to adjust the geometry to give you perfect mode matching. So that's another example of something that you might want to do. Okay, so I was very lucky in this. I became acquainted with a very famous applied mathematician this is when I was at UCLA, a very famous applied mathematician by the name of Stan Osher. And I came to him with a problem. I said, we'd like to do photolithography. So photolithography is the photographic process by which chips are made. And so you could argue this is the most important manufacturing process in the world is photolithography, and people work very hard at it. We had a speaker in the Eeks colloquium maybe 2 weeks ago, and maybe it was last week, and the speaker was an expert on extreme ultraviolet photolithography. And so I told Stan what I was trying to do, and he says, oh, I can do that. I said, what? Like the whole world wants to do this. What do you mean you can do? I can do that, he says. So he showed me what he had in mind, and we ended up starting a company. So to do that, we Luminescent Technologies, and it goes back a little bit, and it became the standard thing to do in the industry. Unfortunately, the founders, who were Stan and myself, did not make any money. Sort of a long story. Well, I'll tell you a little part of that story. Basically, I felt like Intel is a big company. I'm just a professor. And so I went to them and I said, there's this great idea. And I showed them the math. And I was speaking to the head of photolithography at Intel. So at least as a professor, you can get those appointments, okay? The head of photolithography. And he says, oh, you professors, you're always promising to do things and so on, and you never deliver on time, and I don't trust you guys. But he said, I'll tell you what, I'll give you a test pattern. I'm not gonna give you any money. I'll give you a test pattern. You tell us what the negative should look like. So the challenge is, what should the negative look like when you're photographically printing this? And that used to be, the negative used to look like the negative of the thing you were trying to create. But since we are printing sub-wavelength, which has been the case for 25 years, well, not 25, a little over 20 years, we've been printing sub-wavelength. And it's really not clear. If you're just looking at what you're trying to get, it's not all clear what the negative should look like. So there was a challenge there. And Stan said he would do that, so okay. So I'm gonna show you roughly how it's done, and then I'll show you some examples in the photolithography. So now we get into the math slides. And so I gave you the example, the silicon photonic components and mode matching and designing a photolithographic mask. I can tell you what the error was. You print through your printing system, which you have a sort of a photographic printer, and you print and you don't get what you had planned. And so all the deviations around the perimeter of the features that you're trying to achieve, you take the mean squared of all those, add them all up, and that's the error. And that's what you want to minimize, is the mean squared error at the edges, okay? The edges of what you're trying to get. So here is where it gets a little dicey, is we have to go through some math. So we have the figure of merit is going to be like a mean squared error. And I'm going to call it G, but it's a sum of many errors. And of course, G is a function of the electric field that you produce, or the magnetic field, and both. And so usually G, you want a high electric field in one place, you don't want electric field in another place, or you want the electric field to follow exactly a single mode. So that's your goal. So I'm going to write out just Ampere's law, but there's a way to write it with all of Maxwell's equations. But I'm just going to write Ampere's law. So here's Ampere's law that maybe some of you recognize, and you have an input current on the right-hand side. And now, normally, if you talk to people who are sort of mathematical people, to them, this is not Maxwell's equations. Maxwell's equations is a matrix. So that you can write this as a matrix. It's, you can take the matrix, could be all the positions in space that would represent all the terms in the vector. So the electric field, instead of being a 3-vector, you're counting up all the points in space, and you have some gigantic vector of the electric field at every point in space. And the same with the current. And then you have to multiply that with a matrix that represents this differential operator. So the current is a long vector representing current at all points in space. Same thing for the electric field at all points in space. And the matrix is called the Maxwell operator, but basically it captures the derivatives that are in the cross products and everything that are in Maxwell's equations. Okay, so what's your challenge is you want to optimize this G, this figure of merit, but the G is a function of the fields that you're trying to produce. And the fields obviously are a function of position, but they're also a function of the design. So what are your design parameters? Those are P. So you have P design parameters. We said a geometrical shape could have 1 million parameters to define it. Yeah, you could do that. Usually it's less. I think in the splitter I showed you, there were only about 20 parameters. But that was a very simple case. And for a 3D photonic crystal, it's a 3-dimensional shape. So it's quite a few parameters P. And so we're sort of representing them as representing Maxwell's equations as a matrix. And what is our goal is to get the derivative, the gradient of the figure of merit with respect to the design parameters. So we want to change the design parameters to improve the figure of merit. That is to say, we want the local derivative, and if it's getting better, you keep going in that direction. If it's getting worse, you go backward, okay? And so that's the steepest descent that you're looking for. And if you could only just get this derivative, you could do it. You could have the steepest descent. So what I'm about to show you in a couple of slides, and it's going to take 2 slides to get there, is that you can get this derivative very easily by solving Maxwell's equations. Now you say, oh, I don't know how to solve Maxwell's equations. It's not quite true. You can buy commercial Maxwell solvers that solve Maxwell's equations. A lot of companies sell them, okay? So you buy your commercial Maxwell solver, and I'll show you that there's a trick for using your commercial Maxwell solver. You solve Maxwell's equations twice, and you get the derivative, the gradient, at all points in space. So all you have to do is solve Maxwell's equations twice. So that's sort of the trick, and it's kind of a major league trick. So let me kind of show, I'm going to go through the steps then, and to prove that all you have to do is solve Maxwell's equations twice. So first of all, what about the derivative? So we're going to use the chain rule. We want the derivative of the merit function with respect to geometry, and we're allowed to, by the chain rule of calculus, we're allowed to put a differential of electric field in the numerator and also in the denominator. And so we've broken it up into 2 parts. Now, the derivative of the merit function with respect to electric field is kind of easy, because often the derivative of the merit function, I just want to get the biggest electric field at some point. Or I want it to match a single mode. So you know what that derivative is. This one is kind of a hard derivative. The derivative of electric field with respect to the design parameters tends to be rather difficult. And to give you an idea of what's going on, because you're differentiating this one with respect to the design parameters, and there could be 1,000 design parameters, so this one ends up being a vector of length p. The derivative with respect to electric field, it has to do with all the points in space. So that's m points in space. And we have to find this particular, let me erase a few things so we can make it easier to see. Okay, and so this thing is a matrix. It's got M and P, and it's actually a non-square matrix, and it's a column of M and the width of P. So we need to find that non-square matrix. So it's, you just think, oh, how are we going to do that? It's hard. So that one's hard. Okay, so I'm going to show you how to do that. And once we have that one, then we get the whole thing, and we'll end up being able to get the derivative. So I'm going through a few steps here. So first of all, we have Maxwell's equations. Okay. And we can take the derivative with respect to P. So differentiate with respect to the geometrical parameters. And here the derivative of a product is the sum of the derivatives. So we have, first we differentiate this with this, and this we differentiate with that. And the derivative is the sum of the separate derivatives of Maxwell operator and electric field. So we have this, okay. But wait a minute, this is the unknown thing we're trying to find. So let's find it. It's very easy. We just move this one over here. On the right-hand side, we bring this over here. And we get this. And then we have, but we're stuck with the Maxwell operator here. So I'm going to switch to inverse Maxwell operator. So I pull it, M over here, I pull it to the right-hand side, it becomes the inverse. So here I have the inverse Maxwell operator. And this part is very straightforward. It's just the derivative of the currents with respect to the design parameters. The currents could be the design parameters. Could be telling you to have a certain input. So here it is. We haven't made a lot of progress, but we've manipulated a little bit to find this particular non-square matrix. Okay? So bear with me for a minute. I'm going to have to find this thing. This might not be enough information. Let's go on. So here it is again. And this is by the chain rule of calculus, I have the derivative of the merit function with respect to design parameters. And, but I still have the same problem. I don't know what to do with this whole thing. It looks like a mess, so you don't know what to do with it. But I said, oh, this is kind of interesting. What if I group these two terms together? Remember where we got the inverse matrix? We moved it from the left side to the right side, so we got an inverse matrix here. What if I say, that kind of looks interesting. That actually should be a, it should be like a solution to Maxwell's equations. And I'll give you an indication why. It's just by definition now. I've defined this unknown, so this is completely unknown. I just call it lambda, it's unknown. And just the way it's set up with sort of an inverse matrix, that's sort of like multiplying on the right, so I have to use the transverse of that solution to Maxwell's equations. So you'll see in a minute what I'm doing. It's not a, it's a transpose, not transverse, transpose. So I have this, and this is just by assumption. I just put in a random variable. In the spirit of algebra, we put in an unknown. We call this an unknown, and here it is. It's just this particular definition of unknown. And then I move the inverse matrix to the left-hand side, and I get rid of the inverse. I get my matrix back. And in effect, I've multiplied on the right by m. The m's cancel, because it's, and I end up with another equation that looks just like Maxwell's equations. If you remember from the previous slide, this is what Maxwell's equations looks like. And here I have, this is just another Maxwell equation. So that's it. Because I have two Maxwell's equations. If I solve them, I'll be able to get my unknown derivative. Okay, so remind you what I did on the previous slide. I introduced the unknown vector here, and I had it equal to this, and then it ended up looking like Maxwell's equations, and it ended up looking like lambda transverse times the matrix operator, but you can flip that transpose, not transverse, transpose, you can flip that around, and instead of multiplying on the left with the transpose, you multiply on the right with just the a vector that is similar to electric field. And so this becomes the second form of Maxwell's equations, okay? And this is called the adjoint simulation because it started with the adjoint vector and we moved over to the right-hand side. So this is the adjoint simulation. This is the normal simulation of Maxwell's equations. And if you have a Maxwell solver, you solve both of them. They say, well, how can you solve it? You don't know what this is. No, this is very easy. Remember, this is the gradient, the gradient as a function of electric field, and not the gradient, the figure of merit as a function of electric field. And it's very easy to express, so you can just write this out. These are the two Maxwell's equations. And if you get the two Maxwell's equations, here's what ends up happening. And what do you solve? You're solving for lambda, which was the unknown. And now our unknown it replaced this whole thing, which was a mess. We didn't know what it was. And we replaced that. And this term is kind of easy. So the hard term is when this multiplies that. And then, but we have them both. We have the electric field and we have the adjoint solution. So you get the gradient of the merit function at all points in space. And that's sort of the trick. You have your unknown adjoint, you solve for it, you solve for the unknown electric field, you put them together, and you end up getting the gradient of the merit function. So this is kind of a big deal. So what have we done? So the clever application of the chain rule of calculus, you can determine the gradients of merit functions to use for steepest descent, and you only had to solve Maxwell's equations twice. So that's actually kind of a big deal. And so let me indicate this isn't just Maxwell's equations. This is anything else you're trying to optimize. This is very efficient mathematically. And so I asked Stan, my collaborator, Stan, who thought of this? He showed me the math. I said, wow, this is unbelievable. I never saw this before. Who thought of this? He says Gauss. And I say, no, Gauss lived 200 years ago. No way it was Gauss. So we argued back and forth, and I had a graduate student from France, Chris Caroly, maybe some of you remember him, and I asked him, can you find out who thought of this? And he finds me a paper from the early 1900s by a French mathematician, and he translates it for me back into English, and said, no, that wasn't it either. Okay. So finally, we arrived at the decision, who were the first people to do this? So this relates to World War II. So in World War II, General Eisenhower was appointed the Supreme Allied Commander, okay? And why was he appointed the Supreme Allied Commander? If you go back in the history books, this is because he was an expert at logistics. So why are logistics so important in warfare? Is because you win the war if you bring the food, the soldiers, and the bullets together in one place at the right time, okay? That's logistics. And the war ended successfully, and but by the 1950s, the Defense Department was very clear, you need to do logistic optimization, okay? Somehow Eisenhower's team of officers, they figured this whole thing out. You had ships, you had trucks, you had gasoline, you had to bring everything together, and then you had the bullets. And it was very complicated, just getting everything in the right place at the right time. So it was truly a multivariable optimization problem. And I don't know how Eisenhower solved it. And maybe he never solved it, and it just was whatever he came up with was good enough. But by the 1950s, the Defense Department was sort of asking mathematicians, can you solve this? And the only way to solve it, because of the matrices are kind of large, is you need computers. In the 1950s, computers became available. So really the first applications were in the 1950s. And the people who did military logistics were really smart people. They knew the math. And there's actually a department in the College of Engineering. There's an entire department dedicated to exactly this. Okay, we have a department of Industrial Engineering and Operations Research, OR. OR, so this is operations research. This is how to optimize things that you're in the industry, but it could be in the military and so forth, how to optimize things of that sort. So this thing, if any of you are connected or taking classes in OR, this is their bread and butter. The crazy stuff I showed you, the math I showed you in the past 2 slides, is the bread and butter of operations research. So, but they were the first ones. But then it went on. So we go to the 1960s. And this mathematics was adopted for space exploration, because the 1960s was the era that we were sending space probes to Jupiter. And I don't know if you remember what that was like, but they said, well, we're having a mid-course correction. And when to have the mid-course correction, when to start it, when to stop it, you end up with a lot of variables, okay? And then it says, oh, we're in orbit around Jupiter. Whoa, how did you do that? Well, a lot of variables, but by then they had this type of mathematics. Now, I like to call it the adjoint method, because there's a step where you do an adjoint transformation, transpose operation. Adjoint means transpose in linear algebra. And so I call it, but everybody has a different name. And I'll tell you why everybody has a different name for it. And because it keeps getting reinvented in new fields. And each time somebody reinvents it, they say, well, I've never seen this before, and they give it their own name. And so this happens quite a bit, and I'll show you some examples. So, in the 1960s, another important connection to Berkeley, SPICE. So we had in 2012, we had the celebration of the 50th anniversary of SPICE. And it was a kind of big deal, and I went there to meet a few people, and I mentioned this in passing, that I'm trying to find where this came from. And one of the old guys there says, oh, we're already doing this in SPICE. Now, why were they using this mathematics in SPICE? When you analyze an electric circuit, you can just analyze it and everything's fine. But if you're smart about it, you want to do a sensitivity analysis so that, normal resistors are 10% accurate. You don't have a circuit where the circuit only works if you have 1/10 accuracy in the resistors. So they always do a sensitivity analysis of the resistance values to figure out. So they need the derivative. They need that derivative to figure out how sensitive they are. So they were already using this, because it started with logistics and space exploration, but in between, they managed to squeeze it in. He assured me the very first version of SPICE in 1962 already was doing this, not for optimization, but just for a sensitivity analysis. So the word was sort of getting around. And at the end of the 1970s, you could buy a program to do optimization of shapes for mechanical engineering. And in the early days, the US air carriers would not buy from Europe, but they started buying Airbus from Europe. And the early Airbuses, I remember I'd walk down the aisle, and the floor was kind of springy. It didn't feel like a normal rigid floor. It was kind of springy. And apparently they bought this package for structural optimization. So what is it? You want to optimize a shape, use the least weight of material. It's an airplane. You want to use the least weight. And, or if it was a bridge, you could do the least cost. You know, the old bridges, everything was triangles. No optimization, there's just triangles. Today, we would actually have shapes, because this math is available. And in fact, the program was already available by the end of the 1970s. Let me go to the next case. So in the 1980s, it's a fantastic story because everyone is very heavily into artificial intelligence now. And in 2018, an award was given for the introduction of backpropagation. So this was a case, it's the same math, but they didn't realize, or maybe they realized, but they thought it was a neat name. So it's called backpropagation. They call it backpropagation, but it's basically the essence of machine learning and artificial intelligence. And so in the 1980s, it came forward, and you don't have to, maybe some of you, have any of you taken CS 189? Because they're just teaching you what I just was describing. Okay, this is sort of like the first lecture of 189. So I apologize, it's something that's simply not for the very first lecture of the course. Because that's what they do, but they have their own name for it. Now, why are they doing that is because, let's see if I, I'll show you an example. Basically, what you're doing in machine learning, in the early days, it was identifying animals in a photograph. So they would treat the photograph as a vector, but they had to find a matrix that if operated on a photograph of a dog, the resulting vector would be DOG. Okay, if it's a cat, the resulting vector would be CAT. So, and the unknown were all those matrix elements. And you can have a huge, but you have to optimize. Can you imagine 1,000 by 1,000 matrix? Now you're optimizing 1 million variables. So that's why they needed that. Let's go on. So we have, photolithography. I gave you the example of I'll talk more about a photolithography example. Stan and I started the company to do that. And then eventually it goes into deep learning and things where we are today. And another thing that has emerged in electromagnetics is metasurface design, except that they're designing the metasurfaces intuitively the way I did the first photonic crystal, or photonic bandgap. I did it intuitively, and now we say, well, you don't have to do it intuitively anymore. It does not have to be a periodic structure. It could be any shape. You just let the program tell you what the shape is. So this is the litany of how it starts in the 1950s and gets reinvented many times. And often we're changing the name. And we had a CEO for our inverse lithography technology company, and he introduced the word ILT. So ILT is now a common acronym in the photolithography field. I didn't tell you why we didn't make money in that company. Well, I'll get to it. Okay, so here's an example for machine learning. You have a photo, and you have to find all the matrix elements. So if you multiply the matrix elements onto the photo, the vector you get spells out the animal that you saw. So that's a reason. You can see this is optimization, but many variables, because you've got to come up with this matrix. Okay, but it's all automatic now. So co-optimize millions of matrix elements. Okay, now I'm on to the photolithography. Well, the photolithographic mask is usually a chrome film, and then you pattern it, and it's a metasurface, and which pattern is most likely. So it's basically used for making all of today's memory chips and storage chips. Why? Because those are easy to do because they're repeating units, so it's very easy to solve. And this was the company that solved it. And what happened is after I had demonstrated to Intel, it was kind of an interesting story. I had to sign, I had to keep the test pattern secret, and I had to sign that Intel had no obligation to tell me the results, because they were going to pay for making the mask, and it cost a lot of money to make one of those masks. So then I met the Intel guy at a conference in Albuquerque, and he felt kind of sorry that he couldn't tell me. So he says, let's meet at a bar in Albuquerque. So we show up at a bar, and with this conference was in downtown Albuquerque, and there's nobody there in the bar because it's 6 p.m. No one's at the bar yet. And he whips out his laptop, and he says, here are the results. And I look at it, and I say, I can't tell. Is that good or bad? Okay. And he says, well, we've never been able to do random patterns before. So then we started the company. But strangely, Intel never became a customer. It's kind of bad for the company, okay? Intel never became a customer, and later on I found out that because they wanted to develop it themselves, and they did, and they kept it sort of secret, and then they revealed it in 2008. So since 2008, all the microprocessors and the DRAMs and so forth are made using this type of mathematics. This is sort of an example. You're trying to print this, but you end up with totally non-intuitive shapes in the mask. So the solution is rather non-intuitive, and today it's used for DRAM and flash memory since 2005, for the memory applications, and for the microprocessor since 2008. So it's in your laptop, in your cell phone right now. So all of this design optimization requires a figure of merit, and you could have many figures of merit. For the bandgap, it was the bandgap bandwidth divided by the center frequency. But you have many figures of merit: cavity Q, Q divided by cavity volume, minimize back reflection, minimize insertion loss, maximize modulation depth, minimize lens aberrations, maintain achromaticity, which is that it should not depend upon color. So I'll give you an example. This was published 20 years ago, but it's there. We started to optimize. So I'll give you an example, a two-dimensional bandgap, but not an obvious bandgap. The bandgap between band 10 and band 11 for TM modes. And we can also do it for TE modes. So here it is. I would say this particular shape is rather counterintuitive, but there it is. It gives you, it's the 10th band to the 11th band. It gives you a certain gap. And on the other hand, if you're doing TE, the same thing, the 10th band to the 11th band, a little harder to optimize. The structure is also very unintuitive. Okay, and then you have your little bandgap here. So in conclusion, the inspiration and intuition are not reliable. There is an automated mathematical procedure, but this is being adopted in the field. So there are many people who are doing this. I'll mention Stephen Johnson. He's a brilliant professor at MIT, brilliant math professor. He's very heavy. Now he's an unusual guy because math professors usually do not have physical intuition. He understands the physics and he understands the math, so he's in a very powerful position. But there are many of these groups are very heavily into this. And indeed, some of my students, because they learned this method for optimization of nanophotonic components, they go to a company, hires them to do nanophotonics, and they say, you know how to do this. So they switch them over into being into artificial intelligence and machine learning. And so this is a very useful skill. And I would say the combination of understanding the physics and knowing the math is a very powerful combination. So I would recommend it very highly for the students here. And to recommend also, if I haven't already mentioned it, CS 189 or 289. These are courses you can take if you want to go a little bit further. Now, the derivation I showed you was actually from Stephen Johnson from MIT, and I also used some slides from my own former student, Owen Miller, who's a professor at Yale. So thank you for your attention.
All right, we have time for questions, brief questions.
So let me ask a question to you. How many of you are rushing out to take CS 189? How many of you have taken it? Did you already learn some of this stuff? Did you learn some of these things in CS 189?
Yeah, a lot. Actually, that course was taught by Sahai, so we got a lot of assignments to do every week.
I think I can hear you better if your hand is not in your mouth.
He said that the class had a lot of homework. That's the short.
Oh, there's too much homework, okay.
So we need to do a lot of math, like.
Yeah, because what I've done here is like the simplest possible derivation. I did Ampere's law. I didn't do the whole Maxwell's equations and so on. But so this is something I think is very valuable, even if you're a device person, material science person. I think this is something that every undergraduate should learn because it's just a combination of calculus and linear algebra. And it's sort of incomplete. If all you know is how to optimize one variable, that's sort of incomplete. You should be able to optimize many more than one variable.
So Eli, let me ask a question. So was your startup, were you guys the first to do inverse design in photonics?
Yes, basically. But the problem is that people who do metasurfaces, they don't realize that the lithography people are doing metasurfaces first. Okay, so they're a little bit out of touch. But yes, we were the first to bring this mathematics into photolithography. And my evidence of that was the skepticism of the head of photolithography at Intel.
Well, we have an Intel voice here.
That was Jan Bordowski. You know Jan?
You have to get some
but when we came back with the results, and they were good, he said, yeah, this is pretty good. And then he started off that they developed the software internally.
Any other questions?
Okay, we're good.
If not, let's thank the speaker one more time.